for your information. Maybe we can start, since I will be sharing all the recorded classes. You can have an access later. I already shared our lecture notes, the first lecture notes in LMS. And also I shared from the last year's written notes. If you are interested in working in, more questions, you can find it there. So this semester we will be talking about differential equations with you. And you know that you can model everything in algebra. Actually, you can solve your questions. But if you are talking about changing, changing with time, changing with space, you need to have differential equations to be able to model them and analyze them or understand what is going on behind it. And since you will be an engineer, you will be dealing with the things that is changing for sure. That's why differential equations are important for you. I already shared our syllabus with you. I just want to point out a couple more things in here. So our book will be Fundamentals of Differential Equations from Pearson. And we will have 2 midterms, and these midterms will be online with Pearson MyLab, and there will be online homeworks in every week, and we will have a final exam. This has to be 50%. I don't know, I wrote it wrong. Let's change it just in case. Yeah. And I am not giving makeup midterms, so if you have an excuse, your final exam will be also your midterm exam. This is one important point. If you don't have an excuse, you will get 0. And homeworks, I will be assigning homeworks from MyLab online system every week. And also your exams will be on MyLab system. So you need to have this MyLab system. You need to get the text and you can get it from çağlayan.com. I already give you the instructions in here. So how you would get the book. So you need to go to the Çağlayan website. Let me click it if it's working, sorry. Where is that? Here you go. Let me copy paste. I think this is gonna work better. If you copy paste this link in here, it will open the book for you. It is 150 Turkish lira, and once you have it, you will have the registration and the school, course ID into your mail address. Check your mail address. With this code, you can go to the Pearson MyLab and mastering.com, and you need to search our course. Our course ID is here, and you need to register our course, okay? And the access code, again, is gonna be coming to your email once you purchase it. Do you have a question for that? No? Okay. And now let's start our first class. Since we couldn't do the class last week, we need to be a little bit more, careful about the time. So since we are going to be talking about differential equations, you need to remember differentiation and also the integration. So you know what is differentiation means. You did it in calculus, the first derivative, second derivatives, and you know that derivative is a slope of the tangent line at x geometrically. And also once we say dy dt, it means that it is the rate of change of y with respect to t. And in general, this t, what we will be calling is the time. So one quantity is going to be changing with time. So we will be dealing with equations. They have the rate of change of one dependent variable with respect to the independent variable. And since these are going to be, equations that we need to solve, and since there will be derivatives inside our equations, we need to get rid of this derivative to be able to get the function for y. And the antiderivative is the integration. So once you take the indefinite integration, which means that you are doing the opposite calculation to the differentiation. That's why we call this anti-differentiation. Once you take the antidifferentiation of derivative or integral of derivative, you will find the function itself. And also there is a definite integrals. Definite integrals, as you know, what we are finding the area under the curve that is bounded by a and b. So the integral from a to b f of x dx is gonna give us the area under this f of x function between a and b. These are just a little reminder for you. Also, you need to remember how to take an integral, some integral formulations. So these are important for you because we will be using a lot. Differential equations, as I told you, these are the equation containing the derivatives of one or more unknown functions with respect to one or more independent variables. So there will be equations that has derivatives inside. Simple. And these differential equations is started or defined at the later part of the 17th century. And now it's used a lot in different areas like airflow around airplanes or design of airplanes, ship designs, controlling the flight of airplanes, designing medical imaging technologies, designing electric circuits, earthquake detection, wave propagation, and these are just some of the applications of the differential equations, but there are also a bunch of it. Forecasting, you can see also differential equations. So in each area of the engineering, you can find a way of applied in differential equation, okay? And these equations that we are defining for a specific application, what we call these are mathematical models. And these mathematical models that you will see, and actually in our class we will see different part of the mathematical models. Let's start with the first of it. Okay, let's model the free fall. We have an object that has the mass m, and it's falling near the sea level, and we want to find the velocity of this object at any time when it is falling. So let's say this is our problem and we want to model that one. So we have a change. What is it changing? The velocity is changing with time. And which means that our dependent variable will be v, our independent variable will be time. So we have time as an independent variable, velocity v as a dependent variable. And velocity is going to be changing with time. And according to the Newton's second law, you know that force is equals to mass times acceleration. But I'm interested in velocity. So once you use these general laws according to the interest that you are looking for, you need to write your equations in terms of the ones that you want. So I don't want acceleration, I want velocity. That's why instead of acceleration, I can write the derivative of velocity, because acceleration is the first derivative of velocity and second derivative of position, right? You know this relation. That's why I write force as m times dv dt. This is net force. And according to this net force, what we have that is applied to our mass, we have a downward force due to the gravity, which is m times g, mass times the gravitational constant. And also we have an opposite force, that is the force of air resistance, and it is proportional to the velocity with gamma as the air resistance constant. So that force applied to this m is mg, since these are opposite direction, minus gamma v. And this is equals to the net force, Kirchhoff's, you know. All charge has to be conserved. All forces has to be conserved. And if we take g as 9.8, m as 10 kilogram, gamma as 2 kilogram per second, and if we just put it in here and solve for dv dt, here is it. This is a differential equation. This is also what we call as a mathematical model of an object falling in the atmosphere near sea level. Okay, this is your first mathematical model you can think, and we will be talking about how we can analyze it dynamically and also how we can find the solution of these kind of differential equations. So we don't know how to solve it, but we can still have an idea what is going on for this dynamic. Okay. To be able to do that, we will be checking the direction fields of this equation. What is direction field? Direction field, we are looking for, here you go. This is the time, this is the velocity, okay? Time versus velocity. And for each velocity, we will be checking what is the slope of the line that is passing through these specific velocity values. We don't know v, but we know what is v derivative, which means that we know what is the slope. So I can assume that if v is, for example, 10, what do you have? You have something positive, right? And so, and the slope of this at 10, the slope is gonna be 9.8 minus 2, 7.8. And when it is 20, the slope is gonna be less positive, which is 5.8. When it is 30, which is gonna be 3.8. And when it is 49, what is it gonna be? 9.8 minus 9.8, it will be 0. So we have only horizontal lines there. And if you plot these with the arrows, and for each one, check that out, these are just the slopes. And we are showing in each velocity, we are showing the slopes according to the arrows, okay? And it will show you in which initial value, how your velocity is gonna be behaving. So if the initial velocity of your object is 40, then with time, it is gonna be increasing, and the equilibrium is coming at 49. And if your initial velocity is more than 49, you can see that if we start from here, the velocity is going to be decreasing, and again it will reach to the equilibrium after some time. So you can have the idea of the dynamics of your model without solving it by looking at the direction field. Okay? And this is just one example for that. As I told you, this is the equilibrium solution. If the arrows are showing from both ways to your equilibrium, you can say that your equilibrium is stable equilibrium. If they are diverging from your equilibrium solution, you will have unstable. If one part is converging, another one is diverging, you will have semi-stable equilibrium solutions. We will be talking them later. Okay? And how can we find the equilibrium solution? It is easy. You are gonna make your derivative function equal to 0. And you will solve the right-hand side for v. So if this is equals to 0, which means that 9.8 minus 0.2v equals 0, if I solve this one for v, I can find the equilibrium solution. Okay? And in general, for this kind of, this is a linear equation, we will be classifying it a little bit later. To be able to find the equilibrium solution, you are making this one equal to 0 and solve for y. For example, this one, y equals 2 is an equilibrium solution. For that one, y equals minus 3 over 5 is an equilibrium solution. And for this one, you have two equilibrium solutions. One is 0, one is minus 2. Okay? And you can check when 0 and minus 2, for example, when y is negative 1, this is going to be positive, this is going to be negative, so it is negative, so it will be reaching to the negative 2, and it will be diverging from 0. So you can check the equilibrium solutions and how your equation is going to behave between them. And this is another model. Let's talk about it. By the way, if you have question, you can stop me always. Now I don't see the Teams screen, and I can stop and answer your question. Let's consider a mouse population that reproduce at a rate proportional to the current population with a rate constant 0.5. So we have a mouse population, and this population is increasing according to the rate constant 0.5 proportional to the current population. So if your current, let's say our population is P, and this P is going to be changing with time, which means that dP dt. dP dt will be changing with time. How? It is equal to, it will be increasing. Increasing is with the 0.5 rate, 0.5 times the current population P. And when there are owls in the same area, then they will eat the mice. And how they eat the mice? Let's say that the owls eat 15 mice per day. And let's assume our month is 30 days. And let's write the differential equation that is describing the mouse population. So our mouse population is changing with time. It is increasing 0.5 rate proportional to the current population minus 15 times 30, because in each day it is eating 50 times 30, 450. As you can see, this is your second differential equation. Again, this is a linear differential equation. And you can check its equilibrium by making this one equal to 0. If 0.5 p minus 450 is equal to 0, p will be 900. And you can see that at 900 there's an equilibrium value, And if your initial mouse population is more than 900, the mouse population is going to be increasing. But if your initial mouse population is less than 900, then the mouse population will be decreasing. Maybe it will extinct in this area. So you can again change the dynamics by looking at the equilibrium solution and the direction fields. So if we are modeling anything, first you need to identify independent and dependent variables. It is important. And you need to assign letters to represent them. For example, we assign P for mouse population. And our P was dependent variable. Our population was changing dependent to time. So time was independent variable. And also we need to choose the units of measure for each variable. And we need to make sure also each term of your equation has the same physical unit. So it's important. And also you need to know the basic principle that underlie or governs the problem you are investigating. Like in the free fall, we used, the Newton's law. And you need to know these basic laws to be able to model your process. And also you need to know how to express your principle according to the variables that you want. For example, F was equal to MA, but since we were interested in velocity, we wrote our principle with respect to velocity. So this is also important once you are defining your mathematical model. So let's check another example. A certain drug is being administered intravenously to a hospital patient. So they are giving a drug to a patient. And in this drug, it's a fluid, it's containing 5 milligram per centimeter cube of the drug enters the patient's bloodstream at a rate of 100 centimeter cube per hour. So the rate of entering is amount times the rate, 5 times 100, 500 milligram per hour, right? This is the inside, it's going inside. And also this drug is absorbed by body tissues and leaves the bloodstream at a rate proportional to the amount present with a rate constant 0.4. So incoming drug is 500, outgoing drug is 0.4 times proportional to the amount present. If we call the amount of the drug, what did we say? M, then the dt will be 500 minus 0.4 times M. So this is another model for the drug amount. And once you solve this one, you will find the MT, which is the total amount of drug in the patient's body. And once you have MT, you can put time. You can see that after 2 hours, what is going to be the amount of the drug in the patient's blood, or after 5 hours, or after 20 minutes. Depends on you. Once you have this solution, you can find the amount of the drug at any time. And again, if we don't solve it and if we check the equilibrium solution, you will see that after a long time, the amount of the drug is going to be approaching to the 1250 milligram. Within a few hours, it will be reaching to that equilibrium value. So this is another example, okay? And We will be solving those right now. We will be solving in the next class actually by specifying and classifying it. But right now, just for you to understand and the basic calculus, you can solve these differential equations easily. For example, this is our mice and owls equation, and we have a p term here. We have a constant term here. So I am just factoring out the constant in front of the p. So I have a constant term and the p term. Then I will collect the p terms in one side and other terms in other side. So this is a p term. There's a dp here. So I will move this p minus 900 down to the dp, and I will move dt to up there. It's like cross multiplication. So this is going to be same as dp over p minus 900 equals 0.5 times dt. So I have only p variable here. I have only t variable here. This is a separable equation, you can say that. Once you take the integral of each side, the integral of the left is ln p minus 900. Again, please make sure that you remember taking the integral part, okay? You are responsible for that. And if you take the integral for this one, it's just a constant, 0.5 t plus c. And since there is an ln function, I am looking for p. I want to get rid of this ln. So I'm taking the exponential of each side. E to the ln is going to be just 1. That's why we have only p minus 900 here. Right hand side, e to the 0.5 t times e to the c. You can see that. And e to the c is just, again, a constant. And for the absolute value, you can put plus or minus there, and you can get rid of the absolute value also. So what you have, p equals e to the minus 0.5 t times, you can call this is again just a constant. C is just a number, e to the c is just another number. That's why we call that one c, and plus 900. So this is the solution of your differential equation, as you can see. And according to the different initial value, you can get different solutions for this population. Okay? Do you understand this solution? Let me check you. Do you understand this? Okay, great. Then let's continue. Okay, great. Thank you. And as I told you, the integral curves or graphs of solutions for several values of c means that for different c values, you can see different dynamics for the population. And this is just one way to solve it. And for example, for P0850, your solution will be decreasing, decreasing, and decreasing. So how do you apply this P? So if when T is 0, e to the 0 is 1, C plus 900 will be 850, then C will be minus 50. Just put minus 50 here, and your population function is like this. So just put T for any time, and you will find the population of your mice in this area. And this is for if you have this kind of equation, the idea is same. Just factor out the a first, the coefficient of y, and then move the y term under the dy and move dt on the right hand side, which means that collect y terms in one side, t terms in another side, take the integral. This integral will be ln y minus b over a. This will be at plus c. Get rid of the ln by taking the exponential, y minus b over a, e to the at plus c. In here, this is, power, which means that I can write this one as a multiplication, e to the at times e to the c. Since e to the c is just another constant, and I can get rid of the absolute value by putting plus or minus, then I can solve this equation for y, and I can find the solution in general way for this kind of differential equations. Okay? I don't want you to memorize the solution in that way. I want you to put all these steps in a paper once you are solving your exam. Okay? And for the initial value, you can plug in whatever it is given to you, and you can find the solution of your initial value problem in general way like this. And how we wording, since the solution was that, we are plugged in 0 for t, and we are making this equation equal to y0 and solve for c. And whatever we are finding for c, we are putting it in c there. That's why we have this as the general solution of the initial value problem when t is given at 0. And this is the free fall equation. In this one, let's just use the general form of the solution, and this is gonna be the solution when the velocity, initial velocity is 0. At 0 it is 0. Okay, and this is gonna be the solution of your differential equation. B is this constant, A is the coefficient. You are just plugged in here and you can find the general solution, your velocity. And let's look at that. For that one, the solution is starting at 0 is what was that? This is the velocity, right? The velocity is increasing, and for a long time, after a long time, the velocity is going to be reaching at 49. And in there, you can find different solutions. For example, given that the object is dropped from 300 meters above ground, how long it will take to hit ground and how fast will it be moving at impact? So now the initial position is at 300 meters above ground. Okay, you know that, but what you know is the velocity function. But if you know the velocity function, you know how to write this one in terms of the position, because you know that the position's derivative is the velocity. And to be able to find the position function, you are taking the integral of each side. The integral of 49 is 49t. The integral of that one is 1 minus 5 is going down, and exponential function, the constant is coming as a denominator division. That's why we have 445 e to the minus t over 5 plus c. This is our position. And since S0 is 0, c is minus 245. You can find the position function like that. And let t be the impact of time. And when when position is 300, when is it gonna be time? When is it this object is gonna reach to 300? So you will find the t for this equation as 10.51. And if you plugged in this t inside your velocity function, you can find the velocity of this object when it is dropped from 300 meters above ground, and it will take 10.51 seconds to reach to the floor, and the velocity when it reaches to the floor is 43.01 feet per second. Okay, so you can derive different results once you have this solution. Now I will talk about the classification of differential equation, because we will be talking about the solutions and all of these things. So we need to classify, we need to understand the equation first. The first classification is if we have ordinary differential equation or partial differential equations. So we can talk about two different differential equations. One is ordinary, which means that you have only one independent variable. In those two models, velocity was our dependent variable, independent variable was only time. So our derivatives were just a normal ordinary derivatives. That's why we have ordinary differential equations. But if you have two independent variables like partial differential equations, our derivatives will be partial derivatives. For example, heat equation. Heat is depending on time and the position. Or wave equation. These are very common partial differential equations. Again, wave is depending on time and also the position. That's why these are partial differential equations. You can even identify it by the sign of the derivative. These are normal signs, D. These are delta partial derivatives. It has, okay? And we can have systems of differential equations. In that sense, if we have more than two dependent variables. Okay. For example, for the mice and all, if all population is also depending on something, you can add this one into a system and you will have a system of differential equation. We will be talking about the systems at the end of the class. Also, the order of differential equation is the highest derivative. So it is the order of the highest derivative. Look at that, the first one. What is the order? The highest derivative is first order. This one, the highest derivative is second order. So this differential equation is first order differential equation. This is second order. This is fourth order. This is second order because it's taking twice with respect to x. Okay. And linear or non-linear. This is also another classification because for the linear differential equations, especially ordinary differential equations, we can find easily the analytic solution. But once you have non-linear differential equation, you cannot find the exact solution easily. Most of the time, you cannot find the exact solution at all. What do you need? The numeric solution at this time. That's why it is important for you to understand if you have linear or non-linear differential equation. So how do you understand? Look at this form. If your equation is in that form, it is linear. If not, it is not linear, it is non-linear. So what is that form is telling us? The derivative is coming alone. Okay, it shouldn't have any power or root or something. If there is a derivative, it should come alone. And the coefficients of your derivative should be only depend on the independent variable. So these are all t functions. If there is y there, no, you have non-linear differential equation. It can only have t there. Okay. And or also your right hand side, it should be a function of t or 0 or just a constant. Okay. So it says that no power of y greater than 1. So these cannot have any power. No product of y dx, which means that the coefficients of derivatives should not have any include y. It can only have x. No restriction on x. So x can be anything. X can have a root, which means that independent variable can have a root, power, logarithm, sign, it doesn't matter. No restriction on your independent variable. The restriction is on your dependent one for linear equations. For example, this one. Let's classify them if it is ordinary, PDE, order, dependent, independent variable, and linear, non-linear. I'm listening to you. Okay. Tell me, is this ODE or PDE? Is it ODE or PDE? No one? No one is listening to me? Look at the derivatives. And look at how many independent variable you have. It's only x, right? So it's
Yes,
ODE.
yes.
Yes, it is ODE. Thank you. And what is the order? Okay. For ODs, you have Ds. For PDs, you have delta, which means that for ODs, your independent variable is only 1. As you can see here, you have only x as an independent variable. Look at the denominators. And that's why this is ODE, right? We have only x as an independent variable. We have only y as a dependent variable. And our derivatives are normal derivatives. So that's why it is ODE. Is it clear?
Yes, ma'am.
Okay. Then what is the order? What is the highest derivative? 1, 2, 3, 4, 5, 6. Goes on like that. What do you say? What is the order of ODE? The highest derivative term. 2. Yes, it is 2. And as I told you, independent variable is x, dependent variable is y, and it is linear. I told you, I was supposed to ask you. Okay, why this is linear? Look at that. The derivative second order is staying alone, and the coefficient is only depending on x. It works. This one has only 1, and this one is xy. There is nothing wrong in this. So it fits to the form of that one. That's why this is a linear ordinary differential equation, second order. This one, is it ODE, PDE? Is it ODE or PDE?
Teacher,
You have only
PDE.
one derivative term. And this is, again, normal derivative. Look at that. And this population is only depending on time. So it is still ODE. And what is the order?
1.
1. Thank you. It has only one derivative term and it's the first derivative. And our dependent variable is P. Independent variable is?
T.
T. Thank you. And is it linear or nonlinear?
None, I guess.
None. Any guess? It is none, yes, because there is Kp square, right? We said that our dependent variable cannot have power. It should come alone. Look at that. This is Kpp minus Kp square, and this is gonna make our equation nonlinear. Okay? That's one. ODE, PDE. Again, derivative. Only one independent variable. Derivative is just d. It is ODE.
Yes.
What about the order?
2, I guess.
Is it 2?
I don't know.
Is
I can't be
Is
sure.
this mean the order of derivative or square? This is just a square.
Order is 1
Okay.
then.
So if you are showing as the order, you need to put two parentheses around 2. If you see a parenthesis around 2, which means that this is the second derivative. But it takes the parenthesis around the term, which means that this term is square. Okay? That's why this order is 1. Our independent variable is x. Our dependent variable is y. Is it linear? No, because this term has a second power. What did we say? The derivative term should not have any power. It should come alone. No one should touch that term. Okay? That's why this is not linear. Now, is it ODE or PDE? It's obvious, right? Yes? It is PDE, exactly. Because as you can see, we have two independent variables. One is t, one is r. And one independent variable, which is n. So this is, order is 2 because we have second derivatives inside. As I told you, independent variable r and t, dependent variable n. Is it linear? It is linear because as you can see, there this derivative alone, this derivative has an r. It is okay. So k times n is okay. So this is linear. Okay. And please classify these differential equations for yourself and send me the results. I want you to check it by yourself. Okay. And for the solution for the differential equations, which means that if you have a solution, once you plugged in inside your differential equation by taking the derivatives, you need to get 0 at the end, or you need to satisfy this equation. So, for example, for that one, the first derivative of sine is cosine. And if you take the second derivative of sine, which is cosine's derivative minus sine. So second derivative is minus sine, y is sine, minus sine plus sine, 0. Yes, this is the solution. So what you need to do is take the necessary derivatives, put it inside here. If it is equal to the right-hand side, yes, this is the solution. Take the second derivative of that one, minus cosine, sine, cosine. Cosine minus cosine, 0. Yes, this is the solution. And you can try for the y3. Take the second derivative, put it in here, plus y3 should be equal to 0, and you will see that this is also the solution of this differential equation. So you can have different solutions for different initial condition. That's why once we have a differential equation, our important question is if there is a solution. If there is a solution, is it a unique solution? Or if we have analytic solution or numerical solution. These are the three concepts we are working on for the differential equations in general. So you can try by yourself with these models. Let's look at that. Model that one. The rate of change in the temperature T of a coffee at time T is proportional to the difference between the temperature M of the air at time T and the temperature of the coffee at time T. First, you need to read and understand the question, and then try to model. I'm giving you a couple minutes. Yes? Okay, we have the temperature. It's changing with time. So rate of change of in the temperature, which means that you need to write dt, capital T, over dt, which the temperature is changing with time. How it is changing? At a time T is proportional to the difference between the temperature M of the air. So the room temperature at that time is M, and the temperature of the coffee, which is T. So if you say give just some constant, because it's proportional, we don't know, then the temperature with time is changing. M is the temperature, around temperature, minus the temperature of the coffee times some constant K. So you can model your temperature of your coffee. Right now, you can try for your tea after dinner, for example. Change that, check that. And this is an ODE. Order is 1. Independent variable time, dependent variable temperature, and it's a linear ODE because it's just a constant. K is just a constant. This is another question. For example, we have two drivers, Alison and Kevin. They are participating in a drag race. Beginning from a standing start, they each proceed with a constant acceleration. So Alison covers the last 1/4 of the distance in 3 seconds. Kevin covers the last 1/3 of the distance in 4 seconds. And who wins and how much time? So this is another question you can model, you can solve, and you can find who wins this race. What you know is just 1/4 of the distance in 3 seconds Alison covers, 1/3 of the distance in 4 seconds Kevin covers. So constant acceleration. Why am I writing that? Because we know that acceleration is the second derivative of position with respect to time, right? So if it is constant, then A is d square x over dt square. Because this is also dv dt. This is equals d square x dt square. And this is an ODE. This is second order ODE. Independent variable is time. Dependent variable is position, and this is linear. And if you have a linear ODE at any order, you can solve it easily. Okay. So for Alison, you can write this model. You can write this model for Kevin. And the constant acceleration starting from rest implies that just solve this one, which means that take the integral twice. If you take the integral once, it will be the x dt will be a of t plus c. Since the first acceleration is 0, this is c is going to be 0. And if you take integral one more time, you have at squared over 2. So you can solve x by taking integral twice, and you will see that the position is going to be 1 over 2 at squared. And you can solve this for a acceleration, or you can solve this for time. It depends on your problem, what you are trying to find. Since we are going to be dealing with time, this time equation is going to be fit us to solve our problem. So we have Kevin, and it is going to L minus 3, which means that the first to L minus 3. We know the last 1/3 of its rates, how much it takes. And for Ellison, we know 1/4 of the last 1/4 of the race, how much it takes. And if the finish line is in L meters, then the time will be 2L over A. Then what we know is Ellison covers the last 1/4 of the distance. TL minus T3L minus 4. This is for the whole race time. This is for the ones that it covers. The last 1/3 will be equals to 3. If I solve this one for TL, I can find that Ellison is taking 22.39 seconds to finish the race. And if I do the same thing for Kevin and make it equal to the 4, because it takes last 1/3 of the distance in 4 seconds. And if I solve this one for TL, I will see that it takes 21.80 seconds for Kevin. So which one is winning? Of course, Kevin wins the race by about 0.959 seconds. So these are just modeling examples for you to understand how differential equation is working. I already shared these slides with you, and I shared the last year's written notes with you. Also, I want to show the MATLAB part a little bit. If you know MATLAB, I just wrote small things for you. For example, this one is gonna give you the direction field for our free fall equation. Our free fall equation dv dt equals 9.8 minus 0.2v, if you remember it. Let me open that slide for you. It was this, not that one. It was this one. Here you go. So dv dt 9.8 minus 0.2v. So I just defined dv. I opened the mesh grid, which means that I defined x and y integers in a matrix. And with the quiver function, if you run it, you can easily find the direction fields for any differential equation. You can change this one with ovs and mice and do the same thing, but be careful, change the mesh grid x and y boundaries for you, and you can find the direction field of any other differential equation. Okay? And for solution, you can use the solve command for MATLAB. Let me run that. If you run it, it will give you exactly the solution for this one. We already find the solution of that one. Where was that? It was here. Yeah, 49 minus 49e to the minus 2t. If you look at it here, 49 minus 49e to the minus t over 5. Exactly the solution you can find with MATLAB. I will also share these MATLAB codes with you. You can even plot them. If I open that one and run, it will plot the solution if it starts with 0. You can put different, let me put hold on here. Hold on there. So that I can plot the same things again. Let's say our initial velocity is 20. Oh, not here, sorry. I will change in there, 20. I'm changing the initial condition. I say run. See, when it is 20, it will start here and it will reach to the 49 because it was our equilibrium velocity, right? Let's change it bigger than 49. Let me say it's 60 and run. And as you can see, this time velocity is decreasing and it is reaching to the equilibrium. So you can try different initial conditions and you can see how it reaches to the solution like that. Okay. And we can even, let's put this free fall in there to run. So these are the direction fields. Now it's hard to see. We can put the direction field x 0 to 150. Not x, yeah, y, sorry. So you can play with that to get an idea about how the differential equations are working. This is nice, you know, I am just zooming it out so that you can see the arrows and how the solutions are following the arrows like that, okay? So any question? Let me see, I think you have found a question or something. Let me see. Okay. Okay, that's it for today. Not next week, this Thursday, we will be talking about separable equations, linear equations, all kind of solutions. I will share these MATLAB codes with you if you are interested in. And if you will have question, you can ask to me. Make sure that get the my MATLAB access as soon as possible. So I will be assigning your homeworks this weekend. Okay?
Okay, ma'am. As I told you before that I'm not able to join the course on Thursday, so I will try to follow the course from the uploaded videos.
Sure, sure.
Okay.
No problem.
Thank you.
I will take attendance anyways. Doesn't take attendance. Okay. If you don't have any question, I can finalize the class in here. If you will have any question, you can ask to me with an email. Also, I will be at school on Wednesdays and Fridays. If you want to talk, you know, one by one, you can also stop by in my office, okay?
Okay, thank you, ma'am.
Okay.
See you later. Bye.
See you. I'm stop recording now.